This video is going to provide a bit of a review of the idea that we can describe the position of an object in 2 or 3 dimensions by using a vector with multiple components. So let's consider that if I had a vector r of t with components x being some function of t, might describe its position in the I direction, or the horizontal direction. We could have y of t being another function of time that describes its position in the j direction. That would be a vector which could describe the position in 2 dimensions. And if I wanted to, I could go further and describe it in 3 dimensions by saying a third component z of t, another function of time. So then I could substitute any value of t into those 3 components x, y, and z and have essentially coordinates, couldn't I? j, and k values, which would be the coordinates relative to some origin. So consider that could describe the position of an object in 3 dimensions. And we could, tell things about the motion of that object by studying it a bit further, by considering it. Let's consider one just in 2D, which are sort of the main ones that we'll do in this particular application. So I'm going to go just grab the first question from the exercise here. So we've got this vector here, position vector, which is in the form of some trig expression. So 3 cos pi t on 3 is the I component, minus 3 sine pi t over 3 is the j component. We're also told that t is greater than or equal to 0, which I guess makes sense if t is representing time. So in this particular question, we're being asked to find a Cartesian relation that describes the path of that particle. We could sketch that. We could talk about its direction, its domain and range, maybe even where it starts at time equals 0, and so on. So let's start off by saying, well, if x is equal to 3 cos pi t over 3, and y is equal to minus 3 sine pi t over 3, then with just a little bit of rearrangement we could say, well, cos pi t over 3 is equal to x on 3, and likewise rearranging this one we could say sine of pi t over 3 is equal to negative y over 3. And then we could use our trig identity, our Pythagorean identity, which says cos squared of anything plus sine squared of the same thing is always equal to 1, isn't it? So that's our Pythagorean identity on our formula sheet. And so therefore substituting in, well, cos of pi t on 3 was x on 3, so this one here is going to be x on 3 squared. This one here is negative y over 3 equals 1. X squared over 9 plus y squared over 9 equals 1, so the negative will disappear in that process there. X squared plus y squared equals 9. So hopefully we can see there that the path that is being travelled by the particle which has this position vector here, its path is in fact a circle of radius 3. So if we were going to sketch this path is a circle of radius 3. So we are sketching that. So here's our Cartesian relation. So 3, 3, negative 3, and negative 3. Right, now we could say a little bit more about it. We could say which direction it's traveling. We could say where it starts. So let's think about at t equals 0. Well, you can either consider x and y separately, or we could just say r of 0 is equal to, well, substituting in, so for x here, when we substitute in t equals 0 into that one, cos of 0 is 1, isn't it? So it's going to be 3 times 1, so it's going to be 3i, and when we substitute 0 into this part here, sine of 0 is 0, so it's going to be 0j. So in other words, it starts at 3i plus 0j, which is that point there. That's where it starts. And which direction does it travel in? So what we're thinking about is, as t increases, what does this do? Well, regardless of whether it goes that way or that way, x is going to be getting smaller, because cos is going to start decreasing from 1. What about this one here? As t becomes larger from 0, this is going to be heading towards 1, so sine is going to go from the value 0 towards the value 1. So negative 3 times that, it's going to be becoming negative, isn't it? So rather than y becoming positive and it heading this way, it becomes negative and it heads that way. So it's going to be traveling in that direction there. Alright, the domain and the range of this, well, the domain, we can sort of see it from the graph, but also from the function. So the domain is going to be x in the interval negative 3 to positive 3 inclusive. And the range likewise, given it's a circle of radius 3 centered on the origin. Alright, it does ask us one other thing actually in the question, which is the period of motion. So, period of motion. So, remember we can analyze the period of a trig function by looking at this value in here, can't we? So, normally the period of, well, the period of just cos t or sine t would be 2 pi. So period of motion is going to be equal to 2 pi over the b value. In this case, the b value is pi on 3. So can you see that from in here? We've got pi on 3. If we're sort of thinking about transformations of trig functions. So the pi will cancel and we'll have 6 seconds or whatever t is being measured in.